sequences. I know numbers are beautiful. If they aren't beautiful, nothing is. Paul Herodotus. Okay, the numbers are very beautiful numbers. Then Srinivasa Ramanujan was an Indian mathematical genius who was born in Erode in a poor family. He produced thousands of precious formulae, jotting them on his 3 notebooks, which are now preserved at the University of Madras. He is the first research scholar in the mathematics department of University of Madras. He has produced 3,972 formulas and theorems in very short span of 32 years lifetime. He was awarded BA degree for research in 1916 by Cambridge University, which is equivalent to modern day PhD degree. Okay, so that is the history of our Indian mathematician. Now the next one is, next what you are seeing here is some bones. The discovery of it is named as Ishango Bones. Okay, the discovery of Lebombo and Ishango Bones, which existed around 25,000 years ago, was confirmed the fact that human-made counting process for meeting various day-to-day needs. So in this bone some scratches will be there. It represents the numbers, and using the scratches they have to do the addition process and subtractions. Okay, 25,000 years ago they have used these bones for counting. Then another one mathematician, Euclid. Euclid, one of the most important mathematician, wrote important book named Elements. That Elements contain 13 volumes. The first 6 volumes are devoted for geometry. So this Euclid is called as father of geometry. In this lesson we are going to learn this Euclid Division Lemma. What is lemma? Lemma is an auxiliary result used for proving an important theorem. It is usually called as a mini theorem. Lemma means mini theorem. Then his first lemma, theorem 1. If let A and B where A greater than B be any two positive integers, then there exists a unique integer q and r such that A equal to bq plus r, where this q is the quotient and r is the remainder. The remainder lies between 0 and b. 0 less than or equal to r less than b. B is the divisor. Suppose the remainder is 0, we say that it is divisible. B is B divides A, or A is divisible by B. Okay, when the remainder becomes 0, we say that A is divisible by B. That is given in the note. The remainder is always less than the divisor. Usual division also, and the remainder is always less than the divisor. Suppose remainder becomes 0 means then this rule A equal to BQ. That means B divides A. Conversely, if B divides A, then A equal to BQ. Remainder 0. Then the first example problem, we have 34 cakes. Each box can hold 5 cake only. How many boxes we need to pack, and how many cakes are unpacked? Here we using this division lemma, Euclid Division Lemma, we can write this 34 as 5 into 6 plus 4. Usually we are dividing like this, isn't it? 34 divided by 5. 5 cakes. So you have to divide it by 5. So 6 5s are 30, balance 4. So this 34 can be written as 5 into 6 plus 4. Divisor into quotient plus remainder. So 5 6 are 30, 30 plus 4 34. From this, what do you conclude? How many boxes we need? Each box can hold 5 cake. So 6 boxes. Quotient is 6. 6 boxes and 4 cake are unpacked because it is not 5, isn't it? So it is unpacked. So the answer is 6 boxes are required to pack 30 cake with and 4 cakes left over. Okay, children. Then generalized form of Euclid Division Lemma. Generalized form means the same lemma only, but one small difference. This R is positive, 0 less than or equal to R less than modulus of B. Modulus of B means the positive value. So usually the remainder should be positive. If A and B are any two integers, it may be negative also. Then there exists a unique integer Q and R such that A is equal to BQ plus R, where 0 less than or equal to R less than B. That means this B is always, modulus of B means positive value of B. So R lies between 0 and one positive value. So we conclude that R is always positive. That is the generalized form of Euclid Division Lemma. Then next example problem. The first one is find a quotient and a remainder. We have to find out the quotient and a remainder. When A divided by B in the following cases. 3 questions are there. So you have to find out. First question is A equal to minus 12 and B equal to 5. So minus 12 can be written as Euclid Division Lemma. We know that A equal to BQ plus R, where 0 less than or equal to R less than modulus of B. So minus 12 can be written as this quotient, this divisor 5 into, here it is minus. So quotient is always, so quotient is minus. We have to find one negative number and the divisor is 5. So any one number is negative, then only when you multiply you get minus sign. So 5 3s are 15. So you have to take minus 3. So plus 5 into minus 3, you get minus 15. So here it is minus 12, isn't it? So you have to add 1 plus 3. So minus 15 plus 3, you get minus 12. So we conclude that minus 3 is the quotient and the remainder is 3. Remainder is positive value. Okay, children. Then like that, the next question 17 and the divisor is minus 3. So Euclid Division Lemma, A equal to BQ plus R. So similarly you can write this 17 is equal to the divisor minus 3 into, here positive value, the divisor is minus, so minus into minus only you get plus. So 5 3s are 15. So again you have to add 1 2. So you get 17. 15 plus 2 17. This remainder is positive value. Okay. So quotient is equal to minus 5 and the remainder is 2. Then the next question. A is equal to minus 19 and B is equal to minus 4. Euclid Division Lemma says like this. Then substitute the values. Minus 19 is equal to minus 4 into, here you get minus sign. Divisor is also minus. So you have to put on minus plus value quotient. Then only minus into plus you get minus. So 4 5s are 20. You have to take greater value. When the minus sign coming, you have to put on greater value. You have to find out a greater value. 5 4s are 20 minus 20. So you have to add 1 plus 1. So minus 20 plus 1 minus 19. Here R is positive. Okay children. So quotient is 5 and the remainder is 1. So that is the answer. Then for the progress check, quotient is 5, remainder is 1. Then for the progress check, find Q and R for the following pairs of integers A and B satisfying this condition. Okay, similarly you have to find out this 5. You have to find the quotient and the remainder for these 5 problems in the previous examples. Okay, like this you have to find out. Then example 2.3, show that the square of an odd number is of the form 4q plus 1 for some integer q. So show that the square of an odd number, we have to prove that it is in this form. What is the form of odd number? Usually the even number is multiple of 2, isn't it? Simply we can take 2k. 2k is an even number because any number is multiplied by 2, it is an even number. So 2k, even number added with 1, we get odd number. See this x be an odd number. Since any odd number is 1 more than the even number. So we have take this x as 2k is always even. 1 more than this even, it is odd. So we can consider x equal to 2k plus 1 for some integer k. Now the square of an odd number, we can take square of this number. What happened? X square is equal to 2k plus 1 the whole square. It is in the form a plus b the whole square, isn't it? So a plus b the whole square means a square plus 2ab plus b square. So what do you get? 2k the whole square means 4k square. 2ab means 2 into k into 1. 2k into 1. So 2 2s are 4. You get 4k. Plus 1 square is 1 only. From these two terms, you take 4k outside. When you take 4k outside, you get here 1k plus here 1. So now you have to substitute. We have to change it in the form 4q plus 1. So we have to substitute one value for this k into k plus 1. That is q. You can assume it as q. So what do you get? 4q plus 1. So q equal to k into k plus 1. Instead of k into k plus 1, you have to substitute q. So it is in the form 4q plus 1 for some integer q. That is the answer for this question.